Welcome to my talk on a multi-scale theory explaining the initial shrinkage of microporous materials upon absorption. So the motivation behind this study is based on the observation that absorption deformation coupling is ubiquitous among porous materials, whether in nature or in engineering applications. For example, if you put pine cone in dry environment, its scale will open up to release seeds. But if you bring that back to a humidity environment, the scales will close. And the mechanism behind this motion is because some porous tissue along the scale absorb water and expand. So inspired by this observation, material scientists develop porous polymers that can react fast with large deformation upon absorbing of specific type of gases. So this mechanism can be used for designing gas sensors or actuators for robotic uses. So why absorption-induced swelling? Benham gave his explanation that it's all due to surface tension. Imagine a balloon with its tension on the rubber membrane relaxes, then the balloon will naturally expand. Same thing happens during absorption. Even by Gibbs isotherm, it says the more you absorb, the less surface tension it has, then the more relaxed the skeleton is, and it will generate the expansion of the porous material. However, experiment data on microporous materials, which are characterized by pore size of a few nanometers, like activated carbon. However, absorption first introduced shrinkage first, and then followed by Benham expansion. And this shrinkage seems to be observed on a variety of type of gases, and it seems not to be a gas-specific phenomenon. A recent experiment by Bowser repeated the similar test on activated carbon again, with different type of gases as well, and shows the same behavior. So this initial shrinkage cannot be explained by surface tension alone, because we know the gamma only reduces during absorption. To explain this phenomenon, we need to take a closer look at pore scale. So this is a sketch of a macropore, which means it's a relatively large pore. Because of the surface forces that with the origin of van der Waals, electrostatic, or hydration forces, fluid molecules tend to gather together near the solid surface, and resulting in this non-uniform distribution of of fluid density. However, because this pore is relatively large, the middle portion of the pore still resembles the bulk fluid properties. But if you shrink the pore size to micropore regime, then the adsorption regime or the interfacial regime start to overlap. And that means the density profile now becomes this, and there's no region in this pore that exhibit bulk fluid properties. And so the question is, what would be the pore pressure inside this slit pore? And since this is the main difference between micropore and mesopores, we believe this could lead to explanations of the initial shrinkage behavior. So to quantitatively study this assumption, we need to build models. First, we can write down the internal energy of the pore fluid in this way, thanks to Gibbs excess treatment of the fluid inside this pore. You can find this expression in many surface science books. But for micropores, since due to the overlapping, then additional works must be supplied to change the pore size because of that overlapping. So we write it down in this format. It's a function of the pore size, with its conjugated force being the surface area multiplied by a pressure pi. So since the pore size, pore area, and pore volume are related, you can lump this term into the previous two terms and write in the same format as for the mesopores. And you can see that the only difference you need to write to treat micropore than the mesopore is to update the pore fluid pressure to be P plus pi, where the pi is the so-called disjoining pressure or the solvation pressure. Also, the surface tension need to be revised to gamma p, which is you can think as equivalent surface tension. So through Gibbs-Duhem equation, you can arrive at the modified Gibbs isotherm. The reason it's modified is because if you think about large pores where disjoining pressure is negligible, then whatever left is the regular Gibbs isotherm. So it's not that useful, but if you look at its Maxwell relation and integrate, you can obtain the explicit expressions for disjoining pressure and surface tension. So I collectively call them surface force terms because in my notion, they are collective reflection of all the pore scale solid fluid interactions due to the overlapped regimes and so on. So that means, on the other hand, in other words, you just need to know these two terms at in the mechanical aspect to study the consequences of micropore adsorptions. More conveniently, they have a one-to-one mapping related to the adsorption isotherm. And now our task is just to find an adsorption isotherm that is a function of both fluid pressure and the height of the pore. So we come across this paper, Bronner, Deming, and Teller. They are the same team that developed BET theory. They use the same stochastic process that used to derive BET theory to study the adsorption process in a slit pore and come up with the BDDT isotherm. So if you plot this isotherm, you can see that adsorption for large pores, it basically the same as the BET theory, but for small pores, adsorption quickly saturates and flat out because the small pore is easily get filled. So plug this equation back here and do the integration numerically. You can plot the surface forces, such as surface tension as a function of pore pressure. You can see there's no surprise here. It's monotonically decreasing trend, which corresponding to the swelling as explained in Benham theory. But look at the disjoining pressure. You can find that term could be both positive or negative, corresponding to repulsion and attraction. Especially the attractive disjoining pressure happens at low pressure levels and for small pores. And that attractive disjoining pressure in the context of a porous medium will cause a shrinkage of the skeleton. So now we have a competition going on for small pores at small pressure levels. We don't know which effect wins. To study that, we need to build a continuum scale model. So the continuum framework we adopt is the surface pore mechanics framework. It differs from the classical pore mechanics by Cousy or Biot in the sense that the classical ones consider the domain as a mixture of solid phase and fluid phase. But in this work, we also add one more phase. We treat the solid fluid interface as additional phase. It has zero thickness, but it can carry mass, energy, momentum, and so on. And it can do exchange with other phases on these terms. So it's just like an independent phase. So once we do that, you can automatically recover this pore scale forces such as surface tension in the free energy balance of the solid skeleton, which is useful for modeling Benham effect. So the question is whether the micropore energetics can be also recovered in the same framework. So we go through a lot of mass, and indeed we found the free energy balance of the surface active microporous solid can be written in this way. It basically says you can store elastic energy in the skeleton through isotropically compress it, divitorically stretch it, which is the second term, or enlarge the pore by pressurizing and then the conjugated variable is now P plus pi, and or stretch the surface area at which conjugated with the surface tension, the equivalent surface tension gamma P. And this is consistent with what we derived for a single micropore. So a further inspection shows the surface area and porosity are not independent of each other. So you plug this geometrical relation in there, you can arrive at the hyperelastic relation that modified with these two new pressure terms, and they are collectively called adsorption stress. You can think of them as basically the pre-stress installed in the pore skeleton through the interfaces, and adsorption change this pre-stress to cause the shrinkage or swelling of the material. So far there's no material-specific information, but if you want to build a model out of it, you need to specify these components. The surface forces, which are already given once we select the BDDT theory. Then you need to write the elastic energy potential, which we will just pick the simplest linear isotropic one. Finally, we need to specify a geometrical relation. That can be done by considering mono-sized spherical pore. That means all the pore has the same size in the system, and they are spherical. Plug in, you can derive the absorption stress expression, which all comes down to this expression. And this is the mathematical manifestation of the competition that we talked about a few slides earlier. Essentially, it says, okay, compare the reduction of surface tension and attractive disjoining pressure. If the former wins, then this whole term is negative. Plug into the effective stress expression, it will correspond to increasing effective stress, decreasing effective stress, and that's corresponding to swelling. And if the attractive disjoining pressure wins, shrinkage will be predicted. So then you can plug in some common parameters for activated carbon and obtain this shrinkage swelling phase diagram. So this shows that indeed shrinkage is predicted for relatively small pore sizes at low pressure levels. You can also inspect this behavior on the string isotherm. Again, shrinkage only exists for small pores, and once the pore enters the meso regime, there's no such attraction predicted. So we put the model for a case study of Bowser's data. Their specimen is activated carbon. This is a pore size distribution. Apparently, it's a double porosity material, but since we're interested in capture the shrinkage, we pin down the single pore size in the micropore regime. And indeed, the adsorption, the string isotherm is perfectly predicted at small pressure levels and large pressure levels. Especially, the shrinkage is excellently captured. But the adsorption amount is not captured very well. You can see that it predicts very quickly saturated and deviates from the real adsorption data. And to improve the model, we consider the full pore network. So the pore network is now made of many different groups, each group with a unique size. So then the surface free energy is updated to this expression, which essentially replaces the regular surface force terms to their smeared ones, averaged with respect to, weighted with respect to the area or volume. And then we use 107 pore groups to match the PSD of Bowser's data. This is a cumulative one. This is a differential one. This is a cumulative one. And then we run the prediction again. Now you can see that the adsorption isotherm is perfectly predicted. That's thanks to the incorporation of the larger pores, which does not affect too much the adsorption, the string isotherm, but improves the adsorption aspect. So in summary, our model started from intermolecular force considerations, and then we start to consider the structural ordering, density variation near the pore walls in a micropore. And because of that, additional forces generated by this interaction are surface tension and disjoining pressure. So for larger pores, effect of disjoining pressure can be neglected. So surface tension effect alone will cause the swelling during adsorption, as what Benham theory predicted. But for microporous media, the disjoining pressure effect must be incorporated, and it is a competition between these two caused the initial shrinkage swelling transition at low adsorption pressure levels. So our work is now published in IJSS. We just, in fact, finished the proofreading. Please go to that paper if you're interested. Special thanks to my PhD student, Maddie. He's the one that really put a lot of effort in numerical integrations and case studies behind this work. Thank you.